think it's a good time to start today's session. And it's a great pleasure to have our speaker, Dr. Nic Swaronski. He's currently a senior lecturer in the UTS University of Technology, Sydney. And I think I first met him in 2018 in the Asian Pacific Combustion meeting. At that time, very curious to see someone is presenting work about the emission from the wildland fire. So after that, we have a lot of collaboration in this area. And so today, we had a pleasure to have him to talk about these relationship between the fire behavior and the carbon emission, specifically from not just the wildland fire, but also the transportation carbon emission. And I think Nick has also published a lot of work, including in Nature Communication, some high impact fact journals. So I think I'll just give the floor to you so you can give more details.
Sure, thanks for the introduction, Xinyan. Now, hopefully you can hear me.
Yes.
And you can see my slides. Great. Yes, so as Professor Huang was saying, yes, we did meet at an Asia Pacific combustion meeting. So that was in 2019, I think. I remember it well because that's the last time that I've traveled internationally because of the COVID situation. So that was in Japan. Yes, I'd like to thank Xinyan for the opportunity to talk. I think I'd have to probably provide the disclaimer that what I'm going to present today has largely been published a good 5 or 6 years ago, but Professor Huang and myself are actually collaborating on this topic as a result of that conference experience a few years ago. And I think Yu Ying Chen is actually in the audience tonight. So supervising or co-supervising her PhD provides an opportunity to collaborate on this topic. And really what I'm going to be focusing on today is looking at ways of, manipulating fire behavior to try and mitigate, carbon emissions from wildland fire. Quite often seen, wildland fire is quite often seen as a really complicated disturbance, and from a management perspective, a little bit difficult to mitigate. But hopefully after today's talk, you'll get a bit of a feel for some of the options that are available. Okay, so just a few comments I'd like to make here. Wildland fire, for me, is a good topic to work on research-wise for a number of reasons. So fire science and engineering is a pretty interdisciplinary sort of topic. But one thing that I do like about researching wildland fire is that it's a global phenomenon. I'll just bring up my laser pointer. You can see from this, this NASA analysis ultimately that you've got, fire activity in all of the inhabited continents on Earth. So, no wildland fire in Antarctica, but every other inhabited continent has this problem. I guess the fact that wildland fire is a global phenomenon means that irrespective of which continent your career takes you to, there's always the opportunity to do this sort of work. So I like that. The other thing I would say is that wildland fire research is a pretty complicated phenomenon too. It was actually somewhat heartening for someone new coming into this field to hear people with 40 or 50 years of research experience in this particular topic talking about how they're learning new things, or they're still trying to solve challenges or questions that they'd posed to themselves many decades before. So it's not a research area where you get quick success and then you move on to some other topic. It's a good topic to sort of build a career around. The other thing I would say is that from the fire scientist or engineer perspective, a lot of us perhaps have done projects where we're doing research that's relevant to fossil fuels, and globally there's a shift starting to happen to move towards renewable energy sources. And the good thing about researching wildland fire is that if we run, when we stop using fossil fuels, we're still going to have wildland fires. So there's still going to be a position and a role for the fire scientist and engineer to get involved. If there's one thing, I guess this comment probably goes to perhaps the new student or professional who's getting interested in wildland fire. There is actually one document. If you were to read one thing, the one that I really would recommend is this document here. So this one has come out fairly recently. So this is a UN environmental program report, Spreading Like Wildfire. You can find it online. But it actually gives a really nice overview of fire as a global phenomenon. And as I was saying previously, fire is a pretty complicated phenomenon, and it's very difficult to work across the full spectrum of this problem. I should mention that today, really what I'm going to be talking about, I'm going to be focusing on a few things, so which is a subset of the whole problem as a research discipline. So I'm really going to be talking about how you could manipulate ignition processes in what we call prescribed fire in Australia. So a prescribed fire is a deliberately lit fire that you're undertaking for wildland management for a number of purposes. So an intentionally lit fire or prescribed fire might be done to mitigate against wildfire threats. It could be done for ecological regeneration purposes. It could be done for carbon management. You'll see a little bit of that in this presentation, or it could hold cultural significance for traditional landholders and that sort of thing. So I'm really going to be focusing on that bit. Manipulating ignition sources. So it sort of sits under this umbrella of a fuel management strategy. And then the direct link is with environmental impacts. So we're really going to be looking at this from the lens of could intentionally lit fires that need to be done for land management practices anyway actually save a bit of carbon from going into the atmosphere as a result of it. And pretty much the mechanism by which that can happen is that if you've got a prescribed fire and you're actually forming biochar as a product of that fire, the biochar can potentially be stored in soils and sediments for perhaps centuries or millennia, and that's the expense of carbon that's emitted to the atmosphere, largely as CO2. But you can see from this graphic here that this is a bit of a graphical overview of the fire discipline, and you can see that there's all sorts of angles that you can get involved in within this particular topic, which is, as I was saying before, is one of the reasons why I'm so keen on it from a research point of view. And once again, thanks to Shinyan for giving me a push on this, because in recent times I haven't been able to do as much of this work. Should mention that if I mention the term bushfire, apologies in advance. That's an Australianism. So wildland fire, I guess, is the internationally agreed term, but in Australia they're quite often called bushfires. I mean, most Australians live in cities, so the bush is anywhere outside of the cities where 90% of Australians live. So a bushfire is a fire that happens outside of a city. In some respects, you could get overwhelmed a bit with the complexity of wildland fires, especially from a carbon emissions perspective. And you could basically say, well, from a management point of view, perhaps there's not much that we need, well, not much that we're actually capable of doing. I mean, if you have a look in, international carbon accounting documents, they quite often refer to wildland fire, as an uncontrollable or a force majeure event that human intervention can't really achieve much with. But I think from the Australian point of view, we sort of have to confront that challenge head on, because in recent times we've been a signatory to the second Kyoto Protocol commitment period, which did actually end in 2020, so that's 2 years ago. But I think the key point there is that we are accountable for our fires from a carbon accounting perspective. So we've always got to be on the lookout for opportunities to try and undertake carbon emissions abatement from wildland fire. And what I'm going to be talking about tonight in this webinar is really going to focus a lot on carbon accounting, and that may not sound like the most exciting sort of topic to get interested in from a fire perspective. But it's an important one, because if you're going to introduce strategies to manage vegetation, and the work that I'm talking about has application in that area, you need to have a pretty rigorous framework for doing carbon accounting to be able to assess the benefits of an intervention. So in this particular case, I'm going to be arguing that an intentionally lit fire would be an intervention against which some benefits may be able to be achieved. Moving on, I guess that preamble was a little bit on the short side, but I just sort of want to fit in a bit more along the lines of research findings. But most of the experimental work that I've done in wildland fire has been done in this facility. So while my affiliation is University of Technology Sydney, or UTS, this is a facility that I was able to use during my postdoctoral days. And I think there are a number of these sorts of facilities around the world, combustion wind tunnels for looking at wildland fire dynamics. I think the main motivator for this group to develop their own combustion wind tunnel was due to the fact that since about probably early 1950s, I'd say, they had a very strong field-based research program in wildland fire. And one of the big distractions for them was that, because their main research goal was to understand fire behaviour. So they're quite interested in predicting fire spread through the landscape and things like that. One of the big hassles they had was that very rarely did they get weather conditions in the field that were conducive to studying fire, to the point where you could have a big research team located in the bush and have a whole team there for the whole summer and not be able to get burning conditions that were suitable for studying fire. So I guess a combustion wind tunnel avoids those sorts of problems, because as long as you condition the fuel, I guess, to the moisture content that you want, and the ambient temperature and humidity conditions are relatively favourable, you're in a position to do a research burn. Whereas in the field, you have to have the right weather conditions to be able to study that. This facility that I used has recently been moved. So this facility was in Yarralumla, which is in Canberra. That's the capital city of Australia. And you'll notice first thing you'll notice about this combustion wind tunnel is it's got an L shape in it. And when I show you some of the fire behaviour videos in tonight's presentation, what you'll notice is that there is a convection roll in this wind tunnel, which basically means that the flame isn't symmetric about the axis of propagation. Yeah, apologies for that in advance, but that issue has been rectified. This facility is still in Canberra, but it's been moved to Acton. So it's an improved version of this particular wind tunnel. In terms of features, the wind flow is generated by this fan here, fairly large diameter centrifugal fan that weighs a few tons. You've got a flow straightening section in the tunnel just to reduce the turbulence intensity. The working section is actually this part with the glass panels. So this is the section of the wind tunnel where you would prepare a fuel bed. You've got, visual access to the working section itself, so you can do fire behaviour observations. And quite often when we measure emissions, we're measuring downstream of the working section of the tunnel. The tunnel has been used for fire behaviour and suppression studies, and the work that you'll see tonight that I did is looking at emissions from wildland or from our combustion wind tunnel setup. In terms of operating capacity, it's really designed it's not a boundary layer wind tunnel, it's actually upstream of the fuel bed. You've actually got a plug flow that's generated as a result of the flow straightening process. But the target wind speed is a wind speed of 65 kilometres per hour at a 10 metre altitude. Keep in mind that, the real atmosphere has a boundary layer type behaviour. So that really means that a wind speed of 6 metres per second at the surface of the fuel bed would be equivalent to that U10 of 65 kilometres an hour. And you'll see that, that's a wind speed that's relevant for, like a real fire event that occurs in the Australian landscape, but also from an international perspective as well. And the working section itself, you'll see, is 4.8 meters in length and 1.5 meters across. So it's a similar sort of size to some of the previous work that had been done with burning tables in some particular facilities. Okay, so the motivation for looking at the relationship between fire behaviour and potential carbon mitigation really just came off the back of this. So in the Australian Savannah region, which is in the north of the country, so when I say Savannah region, I'm talking about everywhere sort of north of this black line. They've been doing research for about 30 years in partnership with Indigenous landholders to look at how you could manipulate the seasonality of a fire to achieve carbon emissions benefits. And I should pretty much say that at the moment, the sequestration potential of that particular experiment or program, I should call it, probably sits at about the megaton level. So the way this program now works, having done that research 30 years ago, is that there's an LNG company called ConocoPhillips. They invest in this Savannah burning program. I mean, they need to get people on the fire ground to make this happen, but they're typically putting in an investment of a couple of $1 million a year, and they're doing that as a carbon offset measure. And I guess the first question you've probably got at this stage is, how do you actually achieve carbon emissions mitigation here? So when I say Savannah region, definitely in the Australian context, what we're really talking about is a grass tree system. So you've got grass in the understory and you've got trees in the overstory. Now, if you didn't have fire management in play, what could happen is that you would get a late dry season fire, which is really intense. The fuel moisture is very low, and you get these very intense fires moving through the landscape that would actually kill these trees. So if you kill those trees, they don't grow back and they just continue to release carbon. If you shift the fires to the early dry season, the fire behaviour is a bit more manageable. So the fuel's a bit wetter, the fires don't propagate through the landscape as intensely. And what happens is that while you burn the understory of grass, the overstory survives. So the tree survives to next year, it grows a little bit bigger, it accumulates some carbon, and that's pretty much the mitigation potential from this scheme. So while the grass gets burnt annually, the trees are progressively growing bigger and accumulating carbon. And you can see here from this is a satellite data set that goes back to the late 80s in Australia, probably ends a couple of years ago. So you've got fire frequency. So red is 20 to 30 fires over that 32-year record. And you can see that there are some pretty red regions in Northern Australia and the Savannah region. So they're pretty much burning every year or every 2 years. So you can see that from a fire frequency point of view, there's a lot that can be done to try and mitigate those out of control wildfires. So we were using that as a motivator to see what we could do for temperate forests. So we're really talking about this zone in here. And you can see that the dynamics are a little bit different here. We're not getting fires every year. We're getting one fire over that 32-year window. So we tried to figure out what we could do to achieve a similar sort of program in temperate regions in Australia. And when I started, it literally was a blank canvas. And mind you, this was 10 years ago, and I guess some gaps are being filled, but I haven't sort of populated this presentation with those findings. But when I started working on this 10 years ago, there were two references on this topic, how you could manage carbon in a temperate forest in Australia. There was a conference paper, and then there was an honours thesis, which is a black book. It's been stolen from the library in the ANU. So not a lot on this topic. I think in terms of, civilization in Australia, the Indigenous population is a bit more high profile in Northern Australia, whereas in temperate regions, the population there is a bit more dynamic. But what we decided to do, we sort of really looked at existing forestry management practices that were used in temperate forest. And what we found out pretty quickly is that there are a whole range of approaches for controlling the behaviour of a fire in a prescribed fire environment. And that's done by manipulation of the ignition pattern. So there's two good examples here of a chevron burn and a strip head fire. So with the chevron burn, the wind is actually moving from left to right in this figure. And this sort of chevron burn is quite often done on mountaintop ridges and things like that. But you can see here that you've got multiple fire operators with multiple ignition points in the landscape. And as that fire propagates, you'll see that the fire spread mode is altered as a result of this ignition pattern. So for example, you've got parts of the fire that propagate against the wind, which is the fire traveling this way, parts travel with the wind, which is on the downwind direction. You've also got parts of this fire that propagate as a flanking fire, which is perpendicular to the wind. So that would be relevant for this ignition location here. That's a chevron burn. Another common technique that's used is a strip head fire. So in this particular case, the wind is coming from the top of the page to the bottom. Once again, you've got multiple ignition locations, and you've got, well, it's also really good to have a fire break there as a dirt road, but you'll see in this particular case that you've got part of this fire will propagate as a heading fire, propagating with the wind from the top of the page to the bottom. Part of it will propagate as a flank from the left-hand side of the slide to the right. Given that we had these sorts of techniques sitting in forestry management, we sort of thought, well, okay, there could be an opportunity here to try some of these ignition patterns in a combustion wind tunnel and see what sort of impact that would have on not only fire behaviour, but also emissions dynamics. And at this stage, what I'd like to do, I'm just going to stop my share and actually show you, this might be the fun part of the presentation, but show you some videos. So this is, hopefully you can see this. I'll get this playing. Okay, so what you hopefully can see at the moment is a heading fire. It's about to be ignited. So in this particular case, you've got the wind direction is from the right to the left, and you can see that the ignition line is on the right-hand edge of this fuel bed. And once ignition happens, I'll just bring it forward a bit. So you've got ignition, so you've got fire propagation from the right of the wind tunnel to the left. And what you'll see is as this fire propagates, a bit hard to see from an overhead camera, but the flame height is up. The rate of spread is actually, for these particular fuel and wind settings, is quite high. And from an emissions point of view, what you'll notice is as the fire propagates, you actually get quite a lot of smouldering combustion behind the flame front. And once again, I talked about that convection roll in the wind tunnel. You can see that the apex of this flame front doesn't sit symmetrically on the fuel bed. It's actually skewed to the right by about 6 degrees. So that's the price we pay for having a convection roll in the wind tunnel. But yes, you can see the smouldering combustion behind the flame front, and at the flame front itself, flaming combustion with less smouldering involved. Okay, so I think for completeness, I need to show you one more video just so you get the picture of how these fire behaviour experiments are done. So what we want to move to now, so this is a backing fire. So once again, the wind direction is from right to left. You can see that the ignition line is put on the downwind edge, and I'll just play this. Oh yeah, that is playing. Okay, so we've got an ignition at a different part of the fuel bed. Ignition occurs, and the first thing that you notice is that the fire behaviour is quite different. Flame height, you can more or less infer from the overhead view, but flame height is reduced. The rate of spread of that fire is reduced quite a lot. And as I push this video forward, you'll see that we're predominantly looking at flaming combustion here. You're not seeing a lot of smouldering behind the flame front. Rate of spread's reduced, but what you do notice is as this burn continues, that smaller fuel bed is consumed by the backing fire. And I guess for completeness, I could show you the flanking fire, but I better keep pushing on because I'm getting a bit excited already. I've already been talking for 25 minutes, but with the flanking fire, the ignition line is on, I guess, on the left-hand edge of the fuel bed. Wind direction, once again, is right to left, and the flanking fire will propagate through the fuel bed from the top of the video to the bottom. Okay, so that's just to give you a bit of a background on what I'm talking about in terms of manipulating fire spread mode. And if you're interested in quantitative data from this particular experiment, this is more or less what we got. So in these particular experiments, we had a fuel moisture content of about 6%. We had ways of controlling that using an oven. Based on the video analysis, you can do a split of the flaming combustion duration and the smouldering combustion duration. So I always highly recommend to have a camera of your experiment because it facilitates those observations. Rate of spread is recorded. You can do that a few ways. You can use a video feed, and you can use thermocouples with a 250 degrees Celsius temperature threshold. We're measuring combustion factor, so we're not just interested in carbon that's emitted to the atmosphere. We're doing a proper carbon balance. So we're also looking at carbon remaining on the floor of the combustion wind tunnel after the fire. Byram fire line intensity is a measure of the power output from the flame front per unit distance. So you can see straight away that the quicker moving heading fire has a much higher Byram fire line intensity compared to the flanking and backing fires. Charring intensity, very important for biochar production. In a sense, biochar is really all about temperature residence time. And if you want to get charring intensity, effectively what you're doing is you're taking your thermocouple data and you're integrating it. So that's why you've got this 10 to the 4 notation here. So we're sort of saying that temperature residence time would be a predictor potentially of biochar formation. You can also look at time spent by this fire above certain temperature thresholds. So we'd probably call 250 degrees probably roughly flame arrival, and then you can set other temperature thresholds. Time above 500 degrees, time above 750 degrees. And importantly here, what you've got here is this is the emissions ratio for CO over CO2. So that will be related to the modified combustion efficiency. And what you'll notice straight away is that heading fires, by virtue of having all of that smouldering behind the flame front, have a higher CO to CO2 emissions ratio. That's almost sitting at about 14%. Flanking and backing fires, their emissions ratio is quite a lot lower, by a good sort of 40% at least. And you just got a diagram here for how we did these experiments. So this grey bit is where we actually did the pyrogenic carbon sampling. So you can see we've got an array of thermocouples that are positioned around where we did the sampling. And we've also got a consistent way of sampling from these fires when they reached a pseudo steady state. And of course, you've got the reference there for further information if you're interested. Okay, so what we noticed, I probably should have had modified combustion efficiency or MCE on its own slide, but it's a good metric for capturing the dynamics of a fire. So modified combustion efficiency will just be the excess mixing ratio of CO2 divided by the excess mixing ratio for CO and CO2. So if you've got an MCE that's exceeding, let's say, perhaps 90%, maybe 95%, you've got fire dynamics where it's dominated by flaming combustion and you're primarily getting CO2 as an emissions product. If your MCE drops a bit, so for the sorts of fires that we're looking at here, if it drops perhaps, let's say, well below 90%, then you're starting to get a fire where carbon monoxide is building up due to the smouldering combustion. But what we noticed, and this sort of concords with the videos, so this is just the time course throughout the fire, and what you're noticing is that the grey lines and the orange lines in terms of MCE sort of sit a bit higher than the red lines. So these red lines are from the heading fire, and you can see that as these fires progress, In some cases, the MCE is dropping below 80%. So we're getting a lot of smouldering combustion, whereas our flanking and backing fires, it's getting a fairly high and sustained modified combustion efficiency. So we're seeing some differences already in terms of this relationship between fire behaviour and carbon emissions. And if we go a bit further, what we've got here is we're just doing a carbon balance. So we're looking at things that are emitted to the atmosphere, and we're also looking at things that are remaining on the floor of the wind tunnel. And what you'll notice is that by manipulating the ignition pattern and the fire spread mode, you're getting statistically significant differences here. So by avoiding the heading fire combustion, you're getting statistically significant reductions in carbon monoxide emissions. What you're also getting is statistically significant differences in the amount of what probably should have been called pyrogenic carbon. So that's burnt carbon not emitted to the atmosphere, but I've used the, well, not a really great term here, residue carbon. Now, that's when we sort of got a bit more interested in this sort of work, because the burnt carbon that's not emitted to the atmosphere is potentially where a sequestration mechanism sits, and potentially you could manipulate that through changing fire behaviour, because these are some pretty significant increases, like we're talking about, not only statistically significant, but probably about a doubling of the amount of pyrogenic carbon that's remaining. And you can see here that this is just a carbon balance, so it's expressed as a percentage of the total pre-fire carbon. So you're sort of getting, let's say, roughly 70 to 75% of total carbon emitted as CO2. Depending on the fire spread mode, you might get 5 to 10% emitted as carbon monoxide, and then the pyrogenic carbon could be anywhere from 10% up to 20 or 30. But for us, and this is not the order that would make a great story, but we fell into some problems with reporting our data this way. It's one of those interesting things when you sort of publish in a new area of research and people tell that you're wrong. And that was actually a motivator to look at the way of reporting emissions from fire differently. So when you think of, you know, Kuhnian paradigms in science, progress usually goes three ways. People say to you that you're wrong, which is what they said to us, which wasn't very nice. I mean, it's not nice when, you know, a reviewer says that what you're doing is flawed. But once you go back to your calculations and theory and demonstrate that you are right, well, then the reviewer says to you as a second point, this is right, but it's inconsequential. And then as a third step, you know, after the passage of a few years, science progresses to the point where they say, well, we always knew that. And I have to thank a certain colleague for pointing that out to me. But yeah, so it was a bit unusual for someone to express a carbon balance using this, let me just go back again, using this percentage emitted framework. And I think the reason for that is that anyone doing emissions from wildland fire is quite often sitting in the atmospheric sciences community. So while it might be convenient for them to do measurements on the ground or in an aircraft, they're not around the fire site long enough to go onto the fire ground after the fire and investigate the pyrogenic carbon. So once we got to that point and we knew that we didn't make any mistakes, we sort of thought, well, right, we're going to have to do a follow-up study here. And I think in a logical scientific pathway, this work would have happened first, but we weren't really predicting that we'd get an inflammatory reviewer. But this just gives you a diagrammatic overview of, you know, our recommended way of doing this particular accounting. So, I mean, if you're more interested in the carbon balance, really what we're recommending is that instead of just looking at emissions into the atmosphere, at the same time, you would quantify the potential carbon sink that remains on the forest floor. And that's the sort of attitude that would sit well with a biogeochemist. It's not the sort of attitude that would sit all that well with an atmospheric scientist. I mean, they're usually more interested in biomass. They're also quite often more interested in just the bit that's emitted to the atmosphere, and then they look at plume chemistry and things like that. And what we're able to show is that if you do neglect the carbon remaining on the forest floor, well, you're into problems, because your carbon accounting doesn't look great. It's you think of the sort of accounting you do in high school, where it's double entry bookkeeping, and you've got this nice relationship between debits and credits. Carbon accounting from fire, if it's not done properly, it's a shocker. It doesn't conserve mass. You've got things that don't add up, and it really can get messy. But if you can use this accounting framework, you can sort of avoid those particular problems. And it was actually pretty easy to find out where all of this was coming from. We only had to look at a few sort of earlier studies in atmospheric science, and studying those papers pretty much told us where this was all coming from. So I guess most of the authors listed on this page, they're pretty much atmospheric scientists, and you can see here that in multiple parts of this slide, they're making this assumption that all of the carbon that's burnt, I mean, it's thermally exposed to flame and it's thermochemically altered. They're making this convenient assumption that all of it's volatilized, and then they don't have to, bother investigating what remains on the forest floor. So I think by the time we got round to looking at this, we just wanted to try and quantify how large the sink component could be. That became a question that we asked ourselves. I mean, in terms of the accounting framework, we're really just looking for this epsilon parameter. So really, I won't get bogged down in the symbols too much, but we're basically saying that the epsilon component would be pyrogenic carbon remaining on the forest floor. The 1 minus epsilon component is emitted to the atmosphere. And when we started convincing people that this was a better way to do it, we didn't really know what the magnitude of this epsilon parameter was. And I would have to thank my daughter for this. I had a shocker in the kitchen one day, and yes, she said, "Dad, my toast is burnt." And then as soon as she said that, that just helped me to reconcile the sort of stuff that you saw in the atmospheric chemistry community, which is what's listed here, and what at that stage a 4-year-old child says about their breakfast. If a child is complaining of burnt toast, they're not talking about toast that's completely volatilized and all of the carbon and the bread is emitted to the atmosphere. They're just saying it's charred. And it's actually, it's just largely to do with terminology and semantics. But when you looked in some of that earlier atmospheric chemistry literature, that wasn't, something that was consistently done. So that prompted us to do, at that stage, this is 6 years ago now, but a global analysis on what this epsilon parameter could be. And what we found, we could only find 40 studies that did this particular work. But what is interesting is that there is potential in some particular forest types for this epsilon parameter to be quite large. I mean, if you've got a forest type where we're not just talking about burning leaves and twigs and bark, and you've got woody debris, large woody elements on the forest floor, that's the sort of scenario where this epsilon parameter can be quite big. On the other hand, if you're, I should mention, and when that epsilon parameter is quite large, we're really talking about, charcoal formation with a high carbon content. On the other hand, if you're looking at a low epsilon value, you're perhaps looking at a savanna environment where you've got a grassy system being consumed by fire. Combustion efficiency is quite high, and as a result, you're getting largely inorganics or ash being left as a residue, and the carbon content is a lot lower. So you've got a bit of variety in how much carbon can be left on the forest floor. But the important thing is in some cases that parameter can be quite high, and that's important because if the charcoal has the right properties, that's the sort of charcoal that could be stored in soils and sediments for extended periods of time. So our analysis sort of showed that the median epsilon value was about 4%, and it was probably around about that time that my work on this was finishing up. This paper is quite an interesting one. So it actually followed on from that previous study that we did, and actually some global scale analysis was done on what this epsilon value would be. And these authors found that if you did a global analysis, and it was always my intention to do a global analysis, but we had troubles with the Australian government when I was a postdoc. You used to have to get permission from the Prime Minister to go to an international meeting. It was an absolute shocker. But in any event, I had the same idea here, probably about 3 years before this was published, and I always wanted to do this work, but sort of got beaten to the post there. But interestingly, though, at a global scale, they're saying that epsilon value probably sits at more 12%, not the 4% that we were talking about. So that's actually, from a carbon point of view, a way of offsetting some of these emissions. Okay, in terms of pyrogenic carbon, I think you saw the videos before. So you saw this heading fire, the sort of fire that propagates with the wind. I showed you the backing fire video with the backing fire propagating against the wind, and the flanking fires there for completeness. In terms of the pyrogenic carbon, that's when you start, well, you need to sort of unlock some other analytical toolkits. And pretty much our argument here was that temperature residence time was a predictor of biochar formation, and to be able to look at different functional groups within the carbon that we sampled, we did carbon-13 NMR. So if I start talking about recalcitrant or non-degradable forms of carbon, I'm talking about aryl or O-aryl carbon. If I'm talking about more degradable forms of carbon, I'm talking about alkyl or O-alkyl carbon, which is a bit more like a polymer. But that's just a graphical overview of what we're trying to pursue here. And we just really got interested in these post-fire fuel beds. You can see here that we've got a bit of a mix of things going on. We've got clearly some bits that look like they've been charred quite extensively, those black looking bits. We've also got some bits that look a bit more like ash, perhaps a bit more inorganics involved. I should mention that I'm not an NMR expert, but was lucky to be able to collaborate with some people who've probably spent the last 30 years doing this sort of stuff. So, I mean, if you are a carbon-13 NMR person, you can just read what some of these protocols were here. But our main interest is really just looking at what sort of functional groups are present in the carbon. I mean, from a biochar point of view, probably one of the, you would measure you do measure the carbon content post-fire, but it only tells you that carbon's there. It doesn't tell you what type of carbon it is. And if you're looking at the degradability of carbon, knowing what functional group is involved is really important. So if we're having a look at, unburnt fuels that we started with, so one thing you have to do is partition the vegetation into the different fractions. So, the chemistry of leaves, twigs, and bark will be different. I mean, if wood was involved as a fuel in this experiment, you would add that to the list as well. But what you do notice here is that with the unburnt fuel, it's largely dominated by fairly degradable forms of carbon. So you're seeing, for example, that alkyl carbon is quite common in these samples. They're unburnt. O-alkyl carbon is also quite common as well. So generally more degradable forms of carbon. But then again, if you've got lignin in the samples as well, that will be less degradable. Okay, took us a little while to figure it out, but really what we wanted to do here when we did these, pre and post fire comparisons. So what we did is we looked at the carbon chemistry before the fire and after the fire, and after a little while, it became evident that we just wanted to look at the change in carbon as a result of these fires. So really what you'll notice is that any bar that goes below 0, we're talking about consumption. So if you have a look at these different components here, you'll notice that degradable forms of carbon are consumed by fire. So we're talking about the usual suspects. Alkyl carbon is consumed. O-alkyl carbon is consumed, but you've also got bars that go above 0. So that's the one where you've got formation. So the critical point here is that these bars here, this is recalcitrant carbon being formed by the fire. So what have we got? We've got a pretty big contribution here from aryl carbon, but O-aryl carbon is also playing a role as well. And that's what we want to see. We're wanting to see thermochemical alteration of the fuel, and we want to see that fuel ideally converted into non-degradable carbon if we're interested in storing carbon from a fire. Okay, this is just a breakdown for ash. Unfortunately, one of the weaknesses of this experiment was that it probably didn't have enough replication in it to get really great results. This analysis is done in triplicate. You could argue that if we're looking at ash, it's inorganic and it won't have carbon in it. Well, I guess you could say that, but keep in mind that we didn't sort the really fine carbon particles from the ash. You can do that. But yeah, when we did our NMR analysis on ash, we're usually getting an overall carbon content of about 20%, but the carbon is still there. A higher level of replication would help here. I think the 3 other fires that we did things with would have worked better for this experiment, but we did what we could. But we only got one statistically significant result. We did find that there was extra aryl carbon produced by some of the heading fires with the level of replication that we've got. So this is this result here. Got a whole bunch of interesting numerical results. Like, I mean, if we have a look at the backing fires, there's a pretty strong aryl and O-aryl carbon contribution there, but we don't have enough replication in the experiment to say that that's a statistically significant result. And this is the pyrogenic carbon balance. So once again, I mean, if you're doing this sort of work properly, you'll know on the forest floor after a fire, you'll know what your overall pyrogenic carbon balance is, but you can also segregate that between different pools. So I think it's common practice to just split up the fuel types. So once again, we've got leaves, twigs and bark segregated. We've also got ash separated on its own, and any new fuel element that comes into play would also be part of that carbon balance as well. Okay, we did a bit of statistical analysis on this. So we were using principal component analysis, or PCA, to try and understand what the potential relationship was between the different carbon functional groups and the 5 behavior variables. So really, in this particular work, we're quite interested in formation of non-degradable forms of carbon, so aryl and O-aryl carbon. And you can see straight away that any vectors that are roughly parallel are related. So you'll see here that if you're interested in aryl carbon formation, temperature residence time finds its way in there. So the time that you know, that patch of the fuel bed was above 500 degrees is related to that result. The combustion factor is related, the fraction of pre-fire biomass consumed. You can also see that on the other side, Byram fire line intensity potentially has a bit of a role to play, and also the CO to CO2 emissions ratio, which is a metric for how much smouldering combustion that you're getting in your fires. So these results, they sort of hint at what would sound like a sensible biochar production mechanism, but once again have to say that the level of replication would be needed to be increased to increase the level of understanding from these results. But there are some promising signs about the mechanism by which those non-degradable forms of carbon are formed. Okay, I'm in the home stretch now. I guess if you're doing carbon accounting, at some judicious point, you would want to apply these findings to a real fire. And I was lucky to actually get the chance to do some analysis for the 2009 Black Saturday bushfires. So, I mean, the Black Summer bushfires would probably be familiar to some of you, and those fires were sort of characterized a lot by the area that they burnt and how long they burnt for. Like, it was a whole summer of fires. The Black Saturday bushfires, you know, burnt in more or less the same fuel, but the difference here was the intensity. So with these particular fires, this was, well, still is Australia's worst bushfire disaster, 173 fatalities. Byron fire line intensity up to 88,000 kilowatts per metre. So that video that I showed you of the heading fire, that probably had a Byron fire line intensity of 300 kilowatts per metre. These fires were about 250 times more powerful than that. They're all authenticated spotting distances of up to 40 kilometres. So that's when a firebrand travels ahead of the flame front and then forms a fire downwind. So yeah, 40 kilometre firebrand transport. In terms of fire behaviour, weather, temperatures above 40 degrees, 43 degrees Celsius, wind speeds above 90 kilometres an hour. And this is a MODIS satellite image that was taken early on that day. And what makes these particular fires really destructive, and exactly the same synoptic pattern occurred in 1983, which was the Ash Wednesday fires. So in terms of Australian geography, you've got Melbourne roughly down here. That's the capital city of Victoria. And what you quite often get on these days is you get a high pressure system in the desert, a low pressure system off the coast. So that leads to this red section of fire spread, where you've got, in this particular case, you've got a really quickly moving, narrow flame width fire that's propagating through the landscape. But what quite often happens with that synoptic pattern is that you get a cold front will move through and the wind direction will change. And this is what happened in the Black Saturday and Ash Wednesday bushfires. Once this long, narrow heading fire gets changed by the wind direction, it changes into this big heading fire that just sweeps through the landscape. And within a couple of hours, you've got all sorts of problems in terms of loss of life, loss of assets and infrastructure, and fire intensity. So that's what happened in this particular fire event. If you wanted to do emissions accounting from a fire, I guess this all looks pretty straightforward. You just have to use a technique that goes back to Seiler and Crutzen in 1980. You just need to know the area burnt by a fire. You need to know the fuel load. You need to know the combustion factor. So that's the proportion of pre-fire biomass consumed. And you need to know the emissions factor. And that might seem relatively straightforward to do. But the key point is that even after all the fire research that we've done, we've still got really big uncertainties, both in the fuel load and the combustion factor. So if you want to do this sort of work, it very quickly turns out to be an uncertainty analysis due to those uncertainties, as I was talking about before. Emissions factors, on the other hand, and the references on this page are probably the two most relevant global reviews that have been done on fire emission factors. It's interesting, they haven't really changed much in 20 years. So the least important source of variability in this whole calculation is the emissions factor. So while it's quite straightforward to get a nice looking emissions map like this, where most of the work goes is to do the uncertainty analysis and taking into account systematically those uncertainties. You can do a truncated Monte Carlo analysis to come up with what's likely to be a useful estimate for this fire, and that's what this particular work did. So instead of reporting a point estimate for a fire, it's always more important to do an interval estimate. So we managed to get that work done, which was good. Now, actually, to conclude, what I want to say is that I guess if you're talking about bushfires and you look in the carbon accounting field, it can be a bit discouraging to sort of read things saying that wildland fire is pretty much in the climate change world we live in is a bit of a difficult to tame beast. Well, it's not actually quite like that. I think as we look forward, it's quite likely that nature and human activity will do its thing, and fires will be quite destructive. But I think the glimmer of hope is that occasionally nature will get things right in terms of fire. It's not always all about negative consequences from wildland fire, but hopefully this talk might help to stimulate this idea that perhaps human intervention from a fire management point of view may get things right as well. And this picture here, this is actually after the Black Saturday bushfires, and this picture was probably taken a couple of weeks after the fire. And you'll notice that in this particular fire, this rock has been eroded by the fire. It's quite often assumed, I guess, by the general public that these trees will be killed. But even within a couple of weeks of this fire happening, you can see that the tree is resprouting. This tree will grow up to be a big tree again. It's actually one of the amazing features of eucalypt species that they have epicormic sprouts. So this fire will create a rejuvenated forest that will go on to live for another couple of hundred years. But I guess in terms of management intervention, we always just want to be careful that we're introducing things into the landscape that are beneficial. So hopefully the work that I presented tonight might help to kickstart that curiosity, I guess. And if anyone wants to get in touch, thanks for watching the presentation, and look forward to any questions that you might have.
Yeah, hi Nick, here is Tianhao speaking. And firstly, I want to say thanks for giving this impressive and informative lecture. I learned a lot from it. And I know the emission is a great issue to be concerned in fire research. And I was quite impressed by the wind tunnel experiment. Similarly, when we research fire dynamics, when we do some scaled experiments, maybe we need to consider the scaling effect. Maybe we use some similarity law to cover it. Did you use any similarity theory to connect the scaled model experiments to the real fire test, maybe real fire phenomenon? Thanks.
That's a good question. Yes, I think yes. Having a scaling law that sits behind this work would be good. I guess you've got theoretical ways of doing that, but one thing that I've always been quite keen to do is to sort of take this work completely out of a combustion wind tunnel environment and try it in the field. And I think that's something that I'd like to commit to. So, I mean, if you can get these sorts of findings in a field environment, I guess that would be, from an empirical point of view, that would be the best way of addressing that scaling law. But one thing that I would say that's probably worth emphasizing, in some respects, the scaling should work okay. And this is the critical slide right here. I better go back. That's not working the way that I want. A prescribed fire in the field will have a very carefully selected Byram fire line intensity. So at least in the Australian perspective. So you wouldn't find a fire management agency that would want their Byram fire line intensity to exceed 500 kilowatts per meter. And I mean, even though we're only burning a small, bed of vegetation, we are effectively achieving that fire line intensity. So field studies needed, yes. But if the findings do carry across, it could potentially be due to getting this, if you're talking about the scaling on intensity, we may actually be getting that roughly right in a wind tunnel environment.
Yes, that makes sense. Thank you. And by the way, I will host the Q&A season, and we receive some questions from the attendees. The first one is from Yuying. She asked, what fuel did you use and how you get them in the wind tunnel test?
Yes. Okay. Yeah. Thanks for your questions, Yuying. I'm just reading from the chat. So this won't be any exception to your work, Yuying. We're just going to follow the same methodology. You get in contact with a forest management agency. Really what you want to do is just be able to do botanical identification, just to be sure what sort of tree species you are actually collecting vegetation from, and making sure that they're representative of that particular part of the country. That's important. But the fuel collection itself is, I guess you can do a fuel collection from the forest floor. Keep in mind that fire spread is based on what your surface fuels are doing. And then the fire can spread from surface fuels into the canopy, for example, depending on how intense the fire is. But that's what we generally do. It's relatively straightforward to do. So you've got botanical identification, and then you're collecting vegetation in bags. But certain things kick in. You want to make sure that you don't store the fuel for too long. I mean, if you collect eucalypt vegetation and if you transported it interstate, the first thing that you would notice, even after about a day, is that you're starting to lose a lot of the volatile material from the vegetation. So whatever you do, you have to sort of come up with a plan that, you know, if I collect fuel today, I really need to be burning it within a week. Otherwise, if you lose the volatiles from like leaves, for example, your fire behaviour would be different than in a field environment where those volatiles weren't lost. That's the first question.
Yeah.
Okay, I'll move on to the second one. So Ying's also asking, is the emission measurement from the combustion wind tunnel an in situ test? Yeah, it is. So I think in terms of emission sampling, what we were doing is sampling downstream of the working section. So generally sampling probably in this segment here. So 3 or 4 meters downwind of the fuel bed. Now, you've got to be careful with that because you've got to link the measurement technique with what the objectives are. So, for example, if you were interested in plume photochemistry, I haven't done that sort of experiment yet, but you'd have to make sure that you were sampling fresh smoke. If it was aged smoke, then some of those reactions may have already happened and you wouldn't be in a position to measure them. But because you know, we're sampling pretty much near the flaming zone, we are getting fresh smoke, which is good. But there are situations where if you didn't sample fresh smoke, you would get into some troubles. The other thing to think about too is the analytical range of the analyzers as well. So if you were sampling directly from the flaming zone, you would definitely need a pretty good dilution system. You know, depending on what type of spectroscopy you're using, you may not be able to quantify all of the species that you want because the concentrations are much higher. The closer to the smoke you go, the bigger that dilution system needs to be. So we sort of balanced some of those compromises by the sort of approach that we've got here. But the interesting thing is, or the good thing is that in terms of doing the measurements, if you're getting fresh smoke, that's good. But the real saviour though is that the emissions factor is expressed as an emissions ratio. So while your absolute concentrations change quite a lot depending on where you sample, unless you're looking at really reactive species, the emissions ratio won't change much. And that's actually a bit of a saving grace because, I mean, you could sample right above the convection column, or you could sample, you know, if you're in a fume hood environment, you could sample on a stack, you could sample on a stack further downstream. But yeah, it's this emissions ratio that helps to counter some of those differences. There is a third question from you, Ying. Oh, okay. Flaming duration and smouldering duration was done using the video. So yeah, we had a good enough video to know roughly when flames were going out using an optical method. Same thing for the smouldering duration as well. Flaming can be done with the thermocouples. You know, we've used a 250 degrees Celsius threshold for saying that flames are present in a location. Smouldering, you could technically do that from the emissions measurements as well, but flaming combustion will lead into smouldering combustion, and then that will lead into residual smouldering combustion, and then I guess once that's finished, then you would actually say the fire is complete. I got a question from Lee. Okay, I might just read this out for everyone. In your wind tunnel experiments, I wonder if the artificial wind affects the physical complex combustion process. For example, the elevated temperature fails to result in a buoyancy-driven plume rising through the air. Huge influence on the results. Yeah, that's a good question, Lee. That's spot on. That's actually a fairly common criticism that you would make of a wind tunnel experiment. you're right, because a real fire has a convection column. There are potentially ways around that. The facility that I worked in didn't have the capability to do it. But if you've read about the Missoula Fire Sciences Laboratory, they can burn vegetation different ways. So, you know, we can replicate their method of having a combustion wind tunnel that propagates but doesn't have a convection column. But they're also able to do chamber burns where they can retain the convection column. So I think it's direct comparison of those particular methods that could be interesting. And I think from my perspective, if I revisit these experiments again, I'm likely to not use a combustion wind tunnel. It's likely to be in a fume hood. I guess one advantage of doing it in a fume hood is you've got the extraction fan. The extraction fan above can help to generate the convection column. So don't have that data now, Lee, but yeah, that is a good suggestion. It is a common criticism of this work, and hopefully when these experiments get revisited again, there's a chance to answer some of those questions.
Yeah, okay. Due to the time limit, I think that's all for today. And thanks again, Nick, for your wonderful lecture and the question and answer. So for all the attendees, maybe you will receive the certificate in 1 or 2 weeks. Thanks for coming. That's the end. Bye-bye.
Thank you. Thanks, everyone.